So Passive House, a measurable building standard, will be covering some key factors that define healthy buildings with regard to thermal comfort, indoor quality, as well as energy efficiency, and how they can be designed for and measured once buildings are complete and occupied. I don't really have learning objectives, more in a, I put together 4 main concepts to go over with you today. Buildings are for people. Buildings were invented thousands of years ago for people, and the development of the energy discussion about net zero and high performance buildings is losing sight of this. Maybe it's our background as architects, but we always refer to the root of why we build buildings, and that is to provide shelters for people. The second is physics doesn't care. Physics and physics phenomena, including mold, condensation, decay, will happen whether we like it or not. So physics doesn't care about us. We should care about physics. Thirdly, if you can measure it, you can control it. If you know what's happening, you can improve a situation. If you don't know what's happening, then you are guessing. And a lot of what we see in the building science discussion online is that, unfortunately, there's a lot of guessing going on that is not supported by actual science. So today we'll be covering some of the principles of this building science and how they can be monitored on site without diving too much into them. But that is the backbone of Passive House and of proper building science in today's construction. And lastly, long live the simple. If you have ever stepped foot in a construction site, you know that something that is complicated cannot be implemented effectively. You can spend a lot of money and time trying, but if your solution is not simple to begin with, you're going to have a hard time in meeting that expectation. So simplicity is something that happens in Passive House. You push the envelope, and as a consequence, all other pieces become simpler. We're going to see that today. But I think that is a cornerstone of buildings being built better and being durable over time. First thing right off the bat is clearing what Passive House is. It's not passive solar, it's not net zero. Passive solar is a movement started in the 70s or earlier, where people were trying to offset the heat losses through the building envelope by letting the sunshine in, providing passive solar gains. And that is good, and that is part of the foundation and the root of Passive House, but it's not the full picture. Net zero, on the other hand, is kind of the updated version of that, where you do have a certain energy consumption represented on the left side by the infrared image of this house. And you compensate for that energy consumption with renewables. In this case, it's a PV panel. And for net zero, the way the DOE, Department of Energy, has defined it, if your building produces the same amount of energy that it consumes over a year or more, that is a net zero building. That doesn't address at all the quality of the building and the quality of life for people occupying the building. So the whole concept of Passive House is that we improve the building envelope considerably so that the need for heating and cooling is reduced by about 80 to 90% compared to both existing buildings, and even 80% compared to buildings that are built meeting the 2018 Energy Code. Keep in mind that in construction, 2018 is the future. It's 2020, but for construction, 2020 is the future, in that the 2018 building code is still not widely adopted in most of locations in the US. So for Passive House, you greatly improve the building envelope, you reduce the heat losses and reduce the need for heating and cooling by about 75 to 95%. Then you do bring in some passive solar, not a ton. And if you do add renewables, you can get to net zero in a much more streamlined path. The picture on the right-hand side is the Cornell dormitory that is one of the largest passive house buildings in North America, built in New York, for example. So pushing the envelope, the goal is to create buildings that are very suitable, comfortable, and healthy for people. We want to have health, comfort, high indoor quality, durability, and resilience. We'll see later today what that means. And on top of that, we want to have energy efficiency. But the primary goal of buildings is to shelter people. We do that by addressing how the building is built. The photo middle on the right-hand side shows a traditional coffee pot that is made of glass, uninsulated, and it is supplied with heating constantly. The moment you switch the coffee machine off, that coffee loses heat very fast. And that is represented at the bottom right-hand side by the infrared image showing the high heat losses in purple through the glass. Now, you can do better than that, and you can have a building envelope for that coffee that does not have as high heat losses, and that is represented by the thermos on the left-hand side of those images. And that is the whole concept of the passive house building envelope. You have a very well-insulated air-sealed building that minimizes the heat losses, and that works both ways, both in the wintertime and in the summertime. We achieve that by having high thermal insulation, possibly some thermal mass. We're going to address that in a minute. We're going to avoid thermal bridges. We're going to see what they are. Have high quality windows and doors, high indoor quality with filtered mechanical ventilation, and very good air tightness. With these 5 cornerstones, we do achieve a very efficient building that resembles the thermos that we see on the right-hand side. If we do that, the building is going to be extremely comfortable, healthy, and also energy efficient. As part of the background in architecture, we have an experience in designing buildings from scratch. We don't do that anymore, but what we want to stress is how important the design team is, because the way you design buildings is crucial. You are the first energy designer of the building, although it's not in your scope. You deciding what a shape of a building is, where to put glazing, what orientation to give it. It becomes crucial for the energy efficiency of the building. And if you are not aware of this, then it becomes an uphill battle for the building to actually be efficient. The form factor is the amount of square footage of the building envelope, including your ceiling, your slab, your walls, divided by the treated floor area of the building. On the right-hand side, we see a traditional single-family home. The treated floor area is about 1,700 square feet, and the form factor is 3.3. Smaller unit at the top, we have about 300 square feet. This is kind of a tiny house. It was built to be a demonstration house back home in Italy. And because it's so small, the form factor is much higher, 5.5. It becomes more difficult to meet the passive house standard or any energy efficiency, because per square foot of your building, you have more square foot of your building envelope. So the form factor is a very important qualitative number to look at in designing buildings. At the bottom, we see a medium-sized hotel, about 10,000 square feet of treated floor area. And the form factor, just because the building is bigger, it is 2.0. So long story short, the larger the building, the easier it becomes to be more energy efficient. And so if your form factor is high, as shown at the top, the building becomes more expensive and it becomes more difficult to achieve any energy efficiency. And if your form factor is low, it becomes cheaper and easier to achieve any energy efficiency, including passive house. Passive house has the passive in the name, and part of that is passive solar gain. So there is an inheritance from the passive solar movement in passive house, although passive house is much more articulate like a building code. On the left-hand side here, we see a left column that represents all the heat losses in the wintertime through your building envelope. And the column on the right shows the gains. The yellow gains at the top on the right-hand side of the column represent the passive solar gains to the windows. The orange represent the interior gains given out by people and appliances used inside the building. And red shows the active heating. So in residential passive house buildings, the typical ratio is 2:1 gains versus losses. So the gains are in residential passive houses in heating dominated climates. You typically have twice as much passive solar gains than losses. And if you look at the quality of the glass that is used in most American houses, they often have very low solar gains. Solar gains is a quality of the glass that filters out the energy coming from the sun, and you can adjust how much passive solar gains you get. And unfortunately, a lot of American homes are just specified with low solar gains, so you lose an opportunity for free heating, whether or not you want to get to the full passive house standard or not. Now, when it comes to non-residential passive house buildings, including schools, hospitals, offices, they rely a lot more on internal gains. You typically have much higher lighting, much more appliances such as computers, elevators, things like that, that give off more heat. So you need to rely less on the passive solar gains from the sun. This image shows the actual shading provided by a complex geometry outside of a specific glass in Denver, Colorado. You can see in the orange, in this graph, you see the funny shaped mask on the right, and you see the orange and yellow dots. Those represent the apparent sun path in the sky, depending on the season. And you see the kind of triangular white that is the free view of the sky that specific glass pane has through that architectural feature of the building. So in looking at passive house, the building standard, you want to be very accurate in how you model your building, because this relationship with the external environment and your climate becomes very important. Sorry. And one more note about the architecture of the building. While passive solar gains are important, they are, it is possible to achieve very high quality buildings, including passive houses, or what we call PHI, low energy buildings, even if your building orientation is not to due south. Especially in, I'm talking about heating dominated climates. The graph here with the three funny curves shows the heating demand of 3 different buildings. So each line is an individual building. And this is under the assumption that we take the building and rotate that 360 degrees around. And clearly by the rotation that we see at 180, that is due south, the heating demand is the lowest for all of them, because that is the optimum. But you can still get to passive house, even if you have a deviation from due south. For example, the yellow line represents a building built in climate zone 7, so very cold. And the yellow dot shows that the actual building orientation is not due south, is east-southeast. So the orientation of that elevation, the normal to that is 107 degrees. So it's a building that is almost facing due east. But because of the amount of glass and the way it is built, it is still meeting the passive house standard, although it is not facing due south. Going closer to the building envelope, we start seeing thermal insulation providing thermal protection to the building. The underlying concept is that you want to conserve energy before you compensate that via renewables. And if you do that, then you're moving away from the very energy inefficient traditional coffee pot on the right-hand side of the infrared image, and you're moving more and more towards the thermos, the highly insulated, efficient thermos that maintains the temperature. If you have that kind of protection, not only your building is extremely more energy efficient and comfortable, but also it provides shelters to the occupants in extreme weather conditions. If you have a winter blizzard or a heat wave in the summertime, if your building is considerably more insulated, then it becomes extremely more resilient. If the power goes out, your insulation does not stop working. You are still protected. And we'll see at the end of this presentation a test that we carry out in the workshop that we do in teaching builders, and how we prove this concept of thermal resiliency by having a very highly insulated building and letting it out of power overnight. This graph shows a comparison between our values for climate zone 5 between different issues of the International Energy Conservation Code, IECC, and the Passive House Standard. Now, I put this together over the past couple of days, and I was shocked how little code has changed over decades. You see how little the mandatory R values for the prescriptive path, how little they have increased from the 2009 code to the 2018 code. And keep in mind the 2018 code is still the future because it's still not yet widely adopted. So just in looking at how much insulation we could be installing in our buildings if we're going for passive house, and the outcome of that is that the need for heating gets reduced by about 80% compared to brand new buildings. So code is missing a great opportunity, I think, in just jumping ahead and providing buildings with much more energy efficiency. This graph on the right shows the heating demand goals of different passive house standards, starting on the left-hand side with the PHI passive house standard at 4.75 kilobtu per square foot a year. For the Fuse Plus 2018, for the location of Denver, Colorado, we have about 7.9. And PHI, the International Passive House Institute, also has a standard called the low energy building. And that is the heat and demand maximum for that is 9.5. On the right-hand side, we see that how this applies to building retrofits. You can still get to the full passive house standard if you get to 4.75, but if you don't, you can still use all the principles and you can get to an NFE standard at 9.5 kilobtu per square foot a year. So all of this science can be very easily applied to building retrofits. As we'll see an example, a very successful example at the end of this presentation. Thermal mass and thermal storage is something that is highly discussed. This is a brick wall, for example, and the wires that you see going inside the wall is part of a monitoring that we have in place in Colorado. The key of the thermal mass and storage is that it does help stabilizing temperatures a little bit. So it is most effective where you have high temperature swings, that is high loads. And it is effective if the thermal mass is exposed and in direct contact with the internal environment. There are certain type of building assemblies such as the ICFs, insulated concrete formwork, where the thermal mass of the concrete is sheltered from the internal environment by thermal insulation, meaning that that thermal mass is in the middle of your wall and it is not engaged in the thermal environment inside your building. The graph on the left-hand side shows the internal gains comparison between a house and a school. The difference is that a house has very constant internal gains, whereas a classroom, you have kids coming in at a certain time of the day, so you have a peak in occupancy, and then they walk out and there's nobody around at night. So you have very varying internal gains. So what we found, and what we found studying the research done by the Passive House Institute, is that thermal mass is actually underestimated in non-residential buildings. There's a lot of potential in mitigating peak loads if you were to use exposed thermal mass in commercial buildings. Whereas in residential application, as this graph here in the middle shows, the use of thermal mass is secondary in its value for the building compared to thermal insulation. This graph that I'm talking about, the one with the 3 brown columns, shows 3 incremental steps of energy efficiency, so heat and demand, in a building where, starting from the left, you have low mass construction, so stick frame, intermediate construction, so stick frame with a slab on grade, and high mass construction, meaning that the entire building is solid construction with exposed mass. And you see that the brown, that is the active heating, does go down from the left, from the scenario on the left for the low mass to the one on the right-hand side with the high mass, but it does go down minimally. So the use of thermal mass is very efficient if you have to mitigate very varying internal gains. And this graph on the side show the monitoring that we're doing in the brick wall shown in the photo. And those 2 sensors are actually installed on the back of a wall where we have a fireplace in a building. So you can see, especially in the graph at the bottom, you see the solid blue line going up quite a bit. That is the sensor that is sensor number 1 shown at the top, that is installed at 1 inch on the inside of the exposed face brick. And you can see how the temperature penetrated in depth inside the brick. So in this case, masonry is very good at absorbing that high peak provided by the fireplace. Thermal weaknesses, thermal bridging is something that we do care a lot about, mostly because if you have high heat losses, the result is that you have lower localized temperatures in a specific spot of the internal surface of the building, and that opens the ground to more than condensation. If you keep in mind that buildings are for people, you cannot have a good building if you have more than condensation. That is not a high performance building. And unfortunately, code does not cover this effectively. It does cover the second part of the thermal bridging, which is if you have high heat losses, you do have a building performance gap caused by the loss in R value. Code does provide a simplified way to address that, but it does not really address the risk for more than condensation. In this table, we see what we call the temperature factor, FRSI value, that describes the temperature at the bottom of the beam. In that case, it describes the lowest temperature in a thermal bridge. And if you do not mitigate the thermal bridge, you see a temperature factor of 0.648. And depending on the external temperature changes, that temperature can go all the way down to 45 if your temperature outside goes to 0. And at some point along that way, it will be cold enough to cause mold or condensation. That is not acceptable. If you do mitigate that thermal bridge, your FRSI value goes up to 0.90, and your temperature remains high as 63 degrees, even if your external temperature goes down to 0. So this is something that is key in passive house. This is called the hygiene criterion, and it's part of the way you develop the building envelope so that it does meet your climate hardness, and it does provide a mold-free and condensation-free environment for occupants. On the left-hand side, we see a graph of how able is a specific material in causing a thermal bridge. Now, you have insulation that has a certain R value. And this graph shows the ratio of heat losses compared to the same thickness of insulation. Starting from the left, you have insulation, so 1. Softwood with the flow going across the fiber or along the fibers. And I also put the dash boxes to kind of convey who's in charge of looking after that material. So for your framing, you see relatively low, super low ability of wood to cause thermal bridging. So in the discussion right now, we see a lot of care and attention in mitigating thermal bridges caused by wood. But if you look at this graph, those are tiny, tiny mice compared to the big elephant that is metal. So proceeding towards the right on the graph, you see concrete, compared to insulation, concrete can conduct heat about 60 times better. So it can cause 60 times more the heat losses than the same area with insulation. Stainless steel is 425 times more capable than insulation in carrying out heat. Galvanized steel, your fasteners or your steel, like the metal column we see here on the right-hand side, is 1,250 times more efficient at conducting heat and therefore causing thermal bridging than insulation. And aluminum is 4,000 times better than insulation at conducting heat. So if you're looking at talking with your structural engineer, you definitely want to check any concrete or steel cut into your building envelope. And if you're looking at windows or detailing, even just your flashing, you do want to be very careful about any metal penetrating your insulation. This is not about energy efficiency. This is about avoiding molded condensation first and providing high quality buildings to the occupants. Here you see some modeling that we've done on some different types of assembly. In the center, we see a 2x6 wall insulated with zip R sheeting, so supposedly continuous polyiso insulation. And the red dots that you see at the bottom, so many of them, are the thermal bridging caused by the nails. The more you get close to zero energy consumption in buildings, the more every single tiny thing matters. So all those nails that we model according to the spec sheet of that insulated sheeting do cause thermal bridging. As they do cause thermal bridging, the metal fasteners shown in the rainbow picture in the center of the image, where in the blue you see slightly light blue circles, and those are points of higher temperature on the external surface caused by the heat losses to the metal fasteners that are used to install the insulation. The closer you get to zero energy, the more all of this matters. If you're just looking at complying with code, you can just walk away. This is not accounted for. So it's very important if you want to deliver the comfort and the durability and the efficiency that you're designing for, all of this kind of detailing does matter. As it does matter durability inside buildings. Building airtightness equals durability. And this is something that we see a lot of fear and resistance from construction professionals in implementing even just the bare code requirements for airtightness. This is something that has come along recently in building code, starting from before 2012, you could have a very leaky building where you could have as many as 7 air changes per hour at 50 Pascal, and you would still be compliant with code. That means that if your building is, say, 1,000 cubic feet, during the blower door test, shown here on the left-hand side of the slide, during the blower door test, you can measure up to 7,000 cubic feet, and you will still pass. From 2012, Energy Code introduced a mandatory blower door test requirement with a cap at 3 ACH 50 air changes per hour. And that has caused a lot of headaches for professionals because that was never a requirement before. But if you don't have air tightness, then your air can circulate freely through the building assemblies, and you can end up with a situation like we see here, the right-hand side of the slide, with the roof being rotten because of air leaks from the inside of the building carrying warm, moist air inside the building assembly. So the goal of building air tightness in the first place is for the building to be durable. More on the graph in the center, you see that Energy Code has not made any changes to the requirement for air tightness since 2012. So code is taking very small steps with regards to delivering better built buildings. In this slide, we see also air tightness requirement by different Pascal standards, including fuse in this case is around 1.2 ACH. the PHI low energy building is 1, passive house is 0.6, and we see in the field people that do put the time in designing building correctly and air sealing them correctly, you can get as low as 0.14, 1.4. We saw that with builders that first time tried, just in having put the time to review the design and defining that air barrier, they can fairly easy achieve better air tightness than passive house. Air tightness is more about clarity than it is about technicalities. You do need to have very clear goals as far as which air barrier you're using and how that is connected throughout your building envelope. On the right-hand side of this graph, we see in yellow the the air tightness goals for the two passive house standards that apply to building retrofits, including NFIT and the passive house standard, at 1 ACH and 0.6 ACH respectively. And the outcome on the building performance is not only about durability and increased thermal comfort, it's also greatly increasing the energy efficiency. This graph on the right-hand side shows 4 different buildings built in 4 different climate zones, from climate zone 4 to climate zone 7. And they all have different architectural design, glazing distribution, so they are different buildings. But you can see that by how much we reduce the air changes per hour, so the more airtight they become, then the more the heating demand, that is the vertical axis, is reduced. So if you go from 3 ACH 50 requirement of the 2018 code to the 0.6 requirement of passive house, then your heating demand is cut in half. That is extremely important if you want to deliver an actually comfortable and efficient building. And in trying to deliver an actual efficient building, we need to make a comment about building science and how that is carried out. We have an example of a wall that we have, a wall assembly that we have used in a project in climate zone 6. It's a double stud wall with an internal smart vapor retarder, and there is no external insulation. If you were to use the old dew point method in assessing the moisture management of this wall would fail. Now, this column shows the dew point method associated with this old 1930s car, and that's because the dew point method was developed in 1938. Now, building science has come a long way since then, but code has not. So we have a lot of professionals that are still hung up on the dew point method, which is an oversimplified way to address moisture transfer inside building assemblies. There are multiple ways to address this with current building science. And you look at different metrics, including total water content. You do look at the relative humidity inside the insulation and see if you have condensation inside there. But it is only one of the many moisture-driven damages that your building assembly is exposed to. You can have biological decay, for example, what we saw in the roof in the previous slide, and that can happen even if your roof is entirely dry. But if the moisture content of the wood exceeds 20%, that has very little to do with actual condensation. And then you can have other phenomena, including interstitial mold or corrosion, that also can take place without any liquid condensation occurring inside your assembly. The proof of that the advanced building science does work is that we are actually monitoring the moisture content of the sheeting of this wall. And over months of occupancy, this moisture content has never gone up. So this is proof that 21st century buildings do require current building science. As current buildings do require, I don't want to use the word integrated design. It's interrelated design, because it's not that people need to talk to one another. It's a decision made by one person on the design team cause a ripple effect on the design decisions on other people on the team. This is a window, and this is a code compliant window. And unfortunately, there's an expectation that if you do buy a brand new window, you you are going to have thermal comfort, and you are going to have absence of condensation. And that is a very misplaced expectation. That is not true. If you look at the table on the left-hand side, based on the temperature factor FRSI that we covered earlier on about the metal beam that applies to any building component, if you look at this window, the code compliant window, it does comply with the 2018 IECC code. So you can use this in any building in climate zone 5. But because of its poor quality, depending on a combination of external temperature represented by the columns on the table on the left and the internal relative humidity, that is the rows on the left, you can have very easily condensation. Whenever you see on the table the red font, that is condensation. So it's a lot of time of the year. And so the architect specifying this window implies that the mechanical engineer has to put more ventilation to remove more moisture. And this is not something that is clear to the design team today because code does not require this. If you have a high performance window, such as this one, in the same climate, in the same conditions, you never come close to having the same condensation issues. And this is just for hygiene, avoiding mold condensation. There's also something that about windows that a lot of professionals ignore, and that is the quality of the window, the heat losses to the windows are directly related to the comfort or discomfort inside the building. The higher the heat losses, the lower the temperature on the glass, and the higher the thermal asymmetry in the building. So this graph on the right-hand side shows the U values, the heat losses, of windows depending on IECC code, FUSE 2015, 2018, and PHI. And you can see how little code has changed over the past decade. It's shocking, it's very bad. 2015 FUSE did not have any hard requirements for windows, and these requirements were introduced in the 2018 FUSE Plus that became effective about a year ago. And PHI, so if you look at just the numbers, compared to the 2018 code has 0.30 heat losses. The passive house windows are 0.14, so you have less than half the heat losses per square foot. The outcome of that on the thermal comfort is that the temperature on the average temperature on the surface of the window for the brand new 2018 compliant windows, you have about 51 degrees if your room temperature is 68 degrees. And you have about 61 degrees in the passive house window. So about 10 degrees temperature difference. This is not about energy efficiency, this is about thermal comfort. You have 10 degrees higher temperature. And the bottom line is that if you expect cold windows to deliver thermal comfort, you may want to think again. Indoor quality in these days is extremely talked about, and it's something that it is very much addressed in passive house. Code allows up to, talking about the IRC International Residential Code as well as ASHRAE 62.2, they allow up to 75% of air being recirculated. So over a 4-hour period of time, you can pass code with just 1 hour of fresh air and 3 hours of stale air. That is extremely bad for indoor air quality. Whereas for ventilation in passive house, you have continuous filter fresh air with heat recovery. And if you do have the need to recover the moisture, such as in very dry climates, as well as in very humid climates, you have an ERV instead of an HRV. The table on the right-hand side shows the required ventilation rates depending on different codes, the 2018 IECC, ASHRAE, and passive house, depending on the size of the building and occupancy. And compared to popular belief, for single-family houses, ventilation rates for passive house are actually higher than code. In having continuous mechanical ventilation in passive house, you are required to have filters, and the filters at the top right-hand side of the slide show a brand new fresh air filters before being installed. And on the right-hand side, it shows what it looks like after 3 months. So while passive house mechanical ventilation is extremely energy efficient, the goal is to remove pollutants coming in from the outside and delivering constant high indoor quality. Now, we have done some monitoring on the energy efficiency of HRV systems by installing sensors inside an HRV. On the graph, on the left-hand side, at the top, you see the winter performance of this HRV. It is installed in a climate zone similar to US climate zone 4. And you can see a passive heat recovery that the HRV puts in place, preheating for free the incoming air from 30 degrees to 70 degrees. This is done for free through the passive heat recovery core without any active heating. In the summertime, this is also super efficient because, as shown on the left bottom side of the graph, you have a night cooling potential with the HRV bypassing the heat recovery core, providing free night cooling. So these units are extremely energy efficient, although the main purpose of passive house ventilation is to deliver indoor air quality. If you put all of that together, you come about with a building that is actually very simple. So you have a thermos, and from a technology point of view, a thermos is a box that is very highly insulated, but has very few moving parts. Even an HRV or ERV, the ventilator, that is, the moving part in that is just 2 fans. The heat recovery core is static, it does not move. So it's a very simple system. And if you do reduce your heat losses, you need for energy shown on the left-hand side by 75 to 95%, then your mechanicals become extremely small. For this building, this is a building that is under construction in Fort Collins, Colorado. On the left-hand side, we see the weighted average R values according to the 2018 IECC code that are about R12, if you consider all the pieces and weigh the average. In the middle and right on the graph on the left, you see that the average weighted R values for passive house range between 25 to 35, give or take. And insulation is extremely durable. It's very simple. The first modern passive house was built in Germany in '91. In 2016, they did extensive research in the durability of the components by opening up the walls and looking how the insulation was doing. It was doing great. So the expected lifespan of the building envelope components is around 50 plus years. Even the windows, you can expect a lifespan of about 40 years. On the right-hand side, you see the corresponding size of the mechanicals for code built and passive house. And you can see where if you are not putting your effort in the R values, then you do have to put your effort towards the mechanicals. With the downside being that the expected lifespan of mechanical systems, including PV panels, heat pumps, and furnaces and things like that, is considerably shorter. So your money lasts a lot less. And the expected lifespan is around 25 years. The second point about future-proofing your building is the thermal resiliency that is associated with passive house building envelopes. This is a proof of concept that we carry out in the workshop where we teach professionals to build passive house. On the left-hand side, you see these OSB boxes that are nothing but fully enclosed micro buildings that resembles, the passive pods are built to meet passive house in climate zone 5. And we have one baseline code pod that is meeting the 2018 code, also for climate zone 5. And we teach builders and professionals to install insulation, air seal, install windows, and all things like that to deliver the quality of construction that is required for passive house. We do some testing, including infrared and smoke tests as part of the workshop. And at the end of the workshop, the interesting thing is that we do heat the pods and we carry them outside and leave them outside overnight. And we do measure the temperature inside those pods when they are left with no heating. You know, when we do the workshop in Colorado, it typically snows, so it adds to the charm of the test. But what we see is that, as shown on the graph on the right-hand side, the blue line is the external temperature. The gray line is the temperature inside the code pod built to meet the 2018 code. And the orange and brown lines are the temperature inside the chew pod that we're testing in November. And so you end up with the temperature inside the passive building being a full 10 degrees higher than the code-built building if left out of power overnight. So this is thermal resiliency. This is something that protects people and shelters people if the power goes out. This is something that is extremely important in future-proofing our buildings. Just some examples of buildings built around the world. We have the demonstration building built in Italy, some very fancy house in France, Pennsylvania, multifamily project, the Cornell dormitory, as we saw in the very beginning of the slide, and a very large residential project, 3.5 million square feet passive house buildings built in China. These are residential buildings. For commercial buildings, starting from Dubai, an office, there's a myth out there that passive house does not work in warm climates. It's working in Dubai. It has been working in Dubai for a few years now. Museum in Germany, bank in Austria, office building in France, offices in Germany, Austria factory. And you can apply the same concepts to retrofits. We have Germany, Brooklyn, Ontario. So this is something that is extremely valuable for the construction industry to learn about. Just an example of how you can implement this in building retrofits. This building
Enrico, sorry, I don't mean to interrupt. Yes. I just want to make sure we're respectful of time. Do you have a bunch left? Just want to see where you are.
Last one.
Okay, great. I just want to make sure we get to Sharon before she has to go too.
Yeah. So in this building, deep energy retrofit, the need for heating and cooling was reduced by 94% compared to the condition before the retrofit. So there's an incredible potential for improvement in retrofitting buildings to the passive house standard or to the EnerFit standard. So to recap, pushing the building envelope greatly improves the quality of living, durability, and efficiency of buildings. Micro incremental steps of building code are not taking us to our goals fast enough. We saw how little code has changed over the past 10 years, and that is not fast enough to get us anywhere. Physics does not care. If we put physics in a condition to cause damage, physics is going to cause damage. And so physics does not care about us. We should care about physics. And although something may be legal, it can still be a disaster if it's implemented. This is not the future. This is today. This is happening today. That being said, I thank you for your attention, and I'm glad to pass the microphone to Sharon.
Thank you. Yeah, we had a couple of really good questions in the chat window. So if you guys want to stick around, we will stick around a few more minutes and discuss those. But before we end here, I just wanted to quickly introduce Sharon from NAPHN. If she can take herself off mute if she's with us.
I am here.
Hi.
Hi, how are you?
The NAPHN is North American Passive House Network. They're our kind of national organizer for our local group, PHRM, Rocky Mountain Group. And yeah, Sharon, can you tell us a little bit about, we partner with them for training and other things, but can you tell us a little bit about NAPHN as a resource for people looking for more information on passive?
I can. Can I share screen? I just have a couple slides here I can share. Is that all right?
Should be able to. Lindsay, can she share?
Yeah, I got it, I think. Just give me one sec. All right. Can everyone see that?
Yep, looks good.
Great. Hi, my name is Sharon Gabber. I am the Managing Director of NAPHN. Thank you, Enrico and Mariana. So yeah, I just wanted to take a couple moments today to kind of introduce the national organization and how we work with our local affiliates and our regional chapters, which, as Mariana mentioned, Passive House Rocky Mountain is one of our NAPHN chapters. So hopefully you've all heard of us in some way, shape, or form. And hopefully many of you are participating in our conference that's going on. So we are based in New York City, as you can see, my lovely picture. And we are national nonprofit education, and our work is really leading the transformation of the building industry to low energy, high performance, passive house design and construction. And our work is really focused, work is really focused on that kind of inflection point between policy and implementation. So in that space, we're working with governments, leading stakeholders in the building industry, various professional associations, manufacturers, owners, builders, trade organizations, other educational organizations, and amazing manufacturers too, like EMU. So with that, our mission is, how do we move forward with such a kind of lofty mission, is that we do trainings, we put on conferences, we engage and educate the public, whether they're building professionals, policymakers, or the general public. And our particular organization is structured in that we have affiliates, and these affiliates are groups across the US that actually both work in PHI and FIAS. Obviously, we are completely, supported of the Passive House Institute standard, and that is what we work with. And our chapters are all inclusive with NAPHN. So right now we have 5 chapters. We have Rocky Mountain, we have Western PA, Minnesota, New Jersey, and then we have a small kind of new chapter in Washington, DC. So hopefully, we can build, and there'll be many other affiliates will potentially become chapters as we kind of move through. So, the few key assets that we kind of work with is that, we're a resource with this kind of network, and we have collaborative partners with PHI, and we're working with our communities, whether they're national or international. We have the communication infrastructure set up with our websites, newsletters, which you can sign up for, and you can also sign up for PHRM's newsletter. We have, access to these specialized and diverse experts within the field that we kind of bring together, hopefully more than once a year, but definitely once a year with our conference. And we really have that trust and respect of the community at large. So our activities, as I mentioned, education and training are definitely our top activity, and we are proud to be working with EMU as our tradesperson, certified passive house tradesperson partner. It's a relatively new training that we're offering. We've been offering the designer training for a few years now, and we wanted to be able to move into the space with the tradesperson. So we're very excited to be working with EMU on that, and looking forward to picking up after COVID-19. Had some sort of things to adjust, but we're looking forward to a robust schedule. We do work through policy and advocacy, conferences, workshops, and also our publications. So I mentioned before, we have numerous chapters. These are some of our chapters that we work with, and also some of our other kind of regional groups. Like we have a strong connection with Passive House Canada, Maine, the North American Certifiers Circle, Passive House California, Northwest, New York, and also we work with Passive House Academy in Ireland too. And so now we want a little bit reflect for your region, which is one of our, definitely one of our bigger regions. Passive House Rocky Mountain has been, gosh, they've been a chapter for almost 2 years now. So kind of talk about why you'd want to kind of join NAPHN and join PHRM. The big thing is connection. So you want to be able to connect to your network. You want to be able to connect to people, to learn from their experiences and the experience of others. You want to be able to advance your skills. Big thing in our community is to be able to pass that information on to others and kind of lead by example. As Enrico just said, and I think it's a great thing, and I think I'm going to steal it from you, as this is not the future, this is today. So keeping all of that in mind, it's really important to be able to connect with people in your region and see what they're doing. And I'm sure that you may all know that PHRM has a very robust monthly webinar and Zoom call. Definitely join in, get active, and get engaged. So through NAPHN membership, it's a national membership, and then you would become kind of integrated into your local group if you're in the area of the Passive House Rocky Mountains. So obviously, doing that, there's a ton of benefits. You'll be able to strengthen your business connections and your connections in the region, learn new ideas, get new perspectives, be visible, and get local reputation for being an expert in Passive House. There's a lot of good experts in your area, but they're not always known, and it's a large area, so it's good to be able to be out there and talking to people. You can increase your exposure, gain potentially new projects. We are putting up a directory very soon on our website to be able to highlight companies and manufacturers and people that join us as individual members or even corporate members. Corporate members will also get website logo exposure, so you'll be able to hopefully increase your business that way, gain new perspectives, and be able to give advice. So just to kind of tie up a little bit, we do a lot of policy work, and we really rely on regions like PHRM. We started working with the Colorado Energy Office a little bit, and we're hoping to have a little bit more of a robust relationship and get some people not necessarily trained to be designated CPHDs or Ts, but actually get them educated on the basics of Passive House so that they can kind of build it out to the community, and it becomes more integrated within the policy and the code work that we're doing. So if you have any questions, you can definitely reach out to us from the national chapter, naphnetwork.org, or the local chapter is phrockymountains.com. You can reach out to various emails. As I mentioned, EMU is one of our, it's one of our training partners, but is our tradesperson partner. We're happy and very excited to be working with them. If you are interested, we have a few weeks left on our conference. Starts tomorrow, and there's a couple weeks left. I have a discount code here, PH2020, HH15. It's kind of from the happy hour that I'm sure some of you have attended that's been going on. And that is about it. Happy to answer any questions. But if you're looking to get involved with the actual chapter, Mariana, Lindsay, who is the host of this webinar series, and Andrew Michler are three of the leaders for the chapters, and you can definitely reach out to them. We have all their contact information, and they're definitely happy to answer any questions and kind of get you set on the right path. So thank you, and let me know if you have any questions.
Awesome. Thank you, Sharon. Yeah, and if you guys haven't joined in on the conference already, it's been really great. There's still several days left. It's every Wednesday. I think you've only missed 2 of them maybe, but you can log on there at naphnconference.com and join in. So if everyone still has a few minutes left in them, we can open it for Q&A. There have been a couple of really great subjects brought up in the chat window. The first was just very quickly, Enrico, can you quickly address how you see products like AeroBarrier impacting the air sealing market? AeroBarrier was asked about specifically. And we won't spend too much time on that one because I think the other questions deserve a little bit more time, but just your quick thoughts.
So AeroBarrier, for those who don't know, is an air sealing system that is applied to the building by a pressurization test and by releasing vapor of this membrane, liquid membrane that goes in and saturates any air leaks greater than, I think, 1/4 of an inch. My thought on that is that it is a game changer for retrofits, because in air sealing existing frame walls, for example, or existing buildings, you don't get to choose where your air barrier goes or should go. And so that is really exciting to see. I've been promised by AeroBarrier data on the durability of the air seal, and I've not received those yet. So I'm holding my thoughts on that. what is very critical to understand here is that elevator does air sealing. It does not do vapor control. So vapor and air management are two very separate things. And elevator does a great job at doing one, but does not do the other. So in my mind, for new construction, you still want to have smart vapor retarders that are connected and sealed as your air sealing strategy. And then you know that if you fail at meeting the blower door test, there could be a backup option in my mind.
Great. The next question that came up that Lotus asked that I thought was great was suggestions on ways to involve mechanical or HVAC, MEP or HVAC folks into this process a little bit more. We always see fewer folks from the services side joining in on the training, and so ways to engage them.
That is a great question. We have trained now almost 200 builders over the past few years. Not yet one single mechanical engineer. And I think we had maybe one HVAC contractor. So that gives you the share of the market from the mechanical side that is interested in passive house. And that is the same in Europe, to be honest. That is the same experience I had back home. I think it's important to find somebody on the other side of the table that does believe in physics, because we always tell the same story where one of the first large buildings passive house that we worked on, the MEP engineer, we were doing the passive house consulting on the envelope, and the MEP engineer that was just about to retire did not believe the heating load that we had. And our heating load calculated with PHPP, the passive house planning package, that is a software to use to model the passive house, we're accounting for 500 students that we had in the passive house elementary school that we were designing. And if you sum up 500 kids, you get a lot of heat losses, a lot of heating provided by those kids. And that is why commercial buildings, the internal gains are more important than the passive solar gains. On the other hand, the engineer did not believe that. And so we ended up having a mechanical system that was 50,000 euros more expensive, and we lost a bid. That's it. So it's very important to find somebody that believes in physics and not just looks at check boxes. So it's more about finding the right mindset in that conversation.
Did someone try to
ask? Can I chime in on that?
Yeah.
Do you think it's more risky to try to achieve passive house with a mechanical engineer who doesn't understand it than it is to kind of work with a system that they understand and do it best?
Well, just like any goals, if somebody is not in line with the goals of the team, then it's going to be difficult to achieve. So yes.
I think she means, is it risky? Meaning, is it going to present problems if you're trying to reach passive? This is how I'm interpreting it. Lotus, tell me if I'm wrong. But is it going to present any problems if you're trying to reach passive and someone overspecs, you know, a more traditional system kind of a thing?
Yeah, from like a physics standpoint and the durability of the building.
So yeah, in defining the risk for the mechanical system, you may have the simplest one is you're going to have a performance gap. You know, building is supposed to consume X amount of energy, and it consumes more, and that is very likely in the case of an MEP engineer that overspecs. Per se, for the durability of the building and the mechanicals, that is not a huge concern, but you definitely overpay for something that is underperforming, which is not great. And then for the durability, I mean, the loads that we're talking about, heating and cooling loads are lower. The ventilation rates are a little bit, it kind of depends on the use. They're not crazy compared to other type of systems, but it does take some convincing in, hey, you don't need the extra backup boiler of like 80,000 kilobTUs, you know, something ridiculous. Yeah, I think the risk is more in the underperformance than in the physics.
right, in the misalignment of expectations.
For the mechanical system. Does that answer your question?
Yeah, thanks.
Great. Okay, and then before we jump into a really interesting window conversation that's happening over in the chat box, there was another question. Just, Enrico, can you quickly compare the DOE net zero ready energy standard and where passive falls relative to that, and what the difference is, if you can do that in a short version?
So something to be addressed about renewables and passive house. Passive house does address primary energy in that it's targeted towards reducing it. And in DOE language, passive house addresses the source energy and with the target of reducing it. Primary energy for passive house, source energy for the DOE, they are the same concept. What passive house does not require in most of cases you are not required to have renewables to compensate, because the goal is in building a very good building envelope and therefore reducing. The DOE net zero standard is only about compensation. I'm not too familiar with the DOE zero energy ready, honestly. From the name of it, I expect that is relying heavily on compensation, but I'm honestly not too familiar with it in order to draw a comparison in detail.
Okay, great. So, and I can't remember, sorry, who asked that question, but if there's anything that wasn't addressed, either put in chat or take yourself off mute and ask a follow-up. But the last thing was, we've had a little window conversation happen over here. I believe it started because John asked if there were one kind of incremental, or sorry, I'm trying to find the original. So in terms of allocating a project budget, what areas are most important to invest in to achieve passive house goals? And I quickly addressed it by saying windows are super important, but also modeling up front, which doesn't have to cost quite as much as probably what you're imagining. But as far as budget items that always kind of pique the client's interest, the windows are definitely the high price item that comes into that. And a lot of times what we talk about, and I'll let Enrico jump into the building science in a minute, but a lot of times what we try to communicate to our builders who are in training is that we need to kind of shift the way we communicate what we're offering. The product that a builder, a passive house designer or builder is offering is really that entire envelope. And the window is such a key component of making that envelope perform a certain way that it can make or break the final performance of that house or building. And so really kind of shifting the mentality to think about the envelope as the product that you're offering is one way to handle the inclination of clients to want to, cross out the high performance window cost. Whereas if you're trying to reach passive standards, and I think Enrico pointed this out in chat, it's not just about the energy efficiency, right? It's the comfort and the health of the occupants inside. And a lot of times we're not really assessing the correct value to that in our minds ahead of time. Enrico, do you have anything to add?
Yeah, I think what sets passive house apart from other efficiency standards is that the core is that it is built around people and around the climate. So if you have very beefy walls in a cold climate and a double pane window, and if you don't have high temperature inside the window, it may be an energy efficient building, but it's not a passive house because you do not have thermal comfort. So the language here is important. The goal of high performance windows is to match the temperature inside the window and make it so that depending on the climate, you have thermal comfort. So it does not always equate to having triple pane glass. Climate zone 3 and lower, you can have a double pane glass. But the cornerstone is understanding that the window is associated with the thermal comfort. So what I'm hearing is that you only look at energy. To draw a comparison, it is easier to sit on the couch and cheaper to sit on the couch than going to the gym. Going to the gym, you have to pay for. What is the payback of going to the gym? Nothing. Or you live longer and better. What is the payback of eating organic? You pay more and you eat salad, right? I'm kidding. But can you put a price tag on that? You cannot. And so in the equation of looking at the ROI, that is a stupid argument in my mind, because you're losing why we're building buildings. We're building buildings for people. So I get very much not excited about having the most energy efficient building. I'm much more interested in looking at how we can respond to the climate effectively and deliver thermal comfort in absence of condensation. And the reason why there's, you cannot have a passive house if you have condensation. You cannot have a passive house if you do not have thermal comfort, because that is not a good building. So in my mind, it is huge in understanding the value that we're trying to put in building buildings. I hope that was not too
technical terms there.
no,
No, it's good. John, I don't know if you want to take yourself off mute if you needed to follow up on that, but or if he's even still on. But great. Okay, got it. Thanks. Very helpful in chat. Great. Okay, so does anybody else have any other questions for Nico or for Sharon or for me? We have our deadline for the summer crew for training was going to be tomorrow. We're extending that till next week. So if anybody has any questions about that, let me know. But I'll give it just a second and see if anything pops up on chat or if you want to take yourself off mute. And otherwise, I'll let Lindsay say goodbye to everyone.
Can you tell me about your summer crew training?
Sure, yeah. And then there is one other question down there about Climate Zone 7 I just saw. But yeah, the summer crew training, so we, before pre-COVID, we used to do in-person classes, 4-day classes, where we have classroom content and workshop content. We have been able to accelerate getting all of that online. So right now you can take all the classroom content online. It's $475 right now. We're offering live Q&A sessions with that for free. So if you sign up by next week, there's a summer crew that you get to join in, and that means you meet with Enrico once a week on Zoom to go over the units for that week. But you do have on-demand access to it, so you could just listen to the course whenever on your spare time, in your spare time, and on your own schedule. And then we have in-person workshop 2-day units. The next one's going to be scheduled in September here in Denver, and then there'll be another one in November. And those are aligned with the exam dates for PHI for people wanting to take the accreditation course to become a certified passive house tradesperson. I can put our link in chat for you to check it out a little bit more, but really the tradesperson or the builder course is really intended to address things like sequencing and, when you're looking at a set of drawings, what red flags should be going off in your head as far as having to mitigate something farther down the line in order to reach passive. A lot of it is just advanced building science that you can apply to mainstream construction sites as well. But the goal is to really focus on how do you bring the builder farther up into the design conversation so that the impact of implementing this is more easily discussed with the entire team. So we just finished a great workshop with the Lindsays out in the Teton region. So if you check our Instagram, you'll see kind of what that looks like. And then I'll put the link in chat in just a second. Do you have any, was that good, Lizette? Great. Okay. And there's also a preview where you can see all of the course outline and all of the units and the lessons involved with each unit. But, it's everything from thermal bridges, thermal insulation, high performance windows, mechanical ventilation, kind of cover it all. The last question over here, or maybe not last, but one more question from John was, yeah.
Before we jump into the next question, I wanted to point out that the online and the workshop, there are 2 separate pieces of training. So in order to get the training, you do not need to come to Denver or wherever to take the course. You can take the course completely online right now.
Right. We do require, though, that folks coming into Denver for the workshop have done the online portion already because it's such a fundamental part of it. Okay. So John also has a question, Enrico, it's super general. And the answer is yes. Anything specific for Climate Zone 7 to know other than it's difficult?
It's very cold. It's very cold. It is doable. I think we now have at least 3 projects going on, passive house project going on in climate zone 7. You know, either because of elevation or the latitude. It is very cold. It is doable. You know, the more extreme the climate, the more you need to focus on, you know, taking care of the thermal protection of your building. You know, just like climate zone 7, you have probably have a very nice jacket for your wintertime. Same goes for your building.
Is that good, John? We could go on about that forever. The climate zone 7 is really where the window conversation comes into play a lot more too. Okay, any other questions? I see we've got Craig on here. Oh, did he already drop off? Never mind. Oh, and the other Craig, both Craigs. Alpin Craig is there. Tully's here. We've got a couple of former students on here. And then a bunch of people I don't know. Hi. Thanks for having us. If anyone has any other questions, I'll pop our info in the chat.
I encourage everybody to get in touch with EMU Building Science if you guys do have further questions. They're really great trainers. They've helped us tremendously with our Passive House projects. And we're really excited to have you guys join us today and speak about this. And hopefully we can spread the word to more and more of our peers in the industry, and they'll realize that this is within reach in their projects once they start to commit to understanding the building science behind it. So thanks so much for today.
You. All right.
Okay. Everybody have a great rest of your week, and looking forward to seeing you guys next week when I believe we're going to have Toby talk about managing construction waste, correct?
That's correct.
Awesome. Looking forward to it.
Awesome. Thanks,
Okay.
everybody. Bye.
Good.
Good to see you all.
See you soon.
Thank you.